All right, so Cygnus X1, as I said, was the very first one detected. We find these in binary systems where one star has died long ago and there's another star. You need two stars to be orbiting each other for us to get mass information about the black hole, right? And then if this object, because of its orbit around this other object, if the object is 3 times or greater, the 3 times the mass of the sun or greater, then it is a black hole. And the thing that we do detect from black holes is the accretion disk that's around. Let me get my mouse. Where is it? There we go. The accretion disk that goes around the black hole is producing non-thermal radiation, like not black body radiation. Right? Black body radiation is what comes from stars. This is not black body radiation. All right, let's see. So Cygnus X1 they say it's a strong candidate. It's a black hole. Right? If when you do what's called the combined mass, it turns out that the companion to Cygnus is Cygnus X. It's called is about 25 times the mass of the sun, and then the total mass of the binary system is 35 times the mass of the sun, and so therefore this thing, if this is Cygnus X1 right here, it's 10 times the mass of the sun. Anyhow, it's a very small object. So let me say something about okay. So that's what's called a stellar black hole, a single star. It's going to be a massive star, obviously, turning into a black hole. About what was it? Around I think it was about the 1990s. I'm not exactly sure. I don't remember exactly when it was, but it was around sometime in the 1990s. We found that at the center of galaxies, and at first we weren't even looking for this. This occurs many times in science, where there's something you're not even looking for, and you find something completely unexpected. At the center of galaxies, it turned out that there was an object that has since been called a supermassive black hole. So these are things that have of the order of more than 1 million. In fact, this is, I don't know why they're saying just 1 million, right? The supermassive black hole at the center of the Milky Way is like 5 million times or something like that, 4 to 5 million times the mass of our sun. So that's a supermassive black hole. But there are other galaxies out there that have at the center of their at the center of those galaxies there is an object that has some of them approach 1 billion times. So 1 times 10 to the 9th times the mass of the sun at the center of some of those galaxies. So those are called supermassive black holes. So stellar black holes, that's what we were talking about. Supermassive black holes, we're not exactly sure how they form, although as we're going to see when we start talking about galaxies, we think that really galaxies probably form because the supermassive black holes form. Anyhow, there seems to be a relationship between the size of a galaxy and the supermassive black hole at the center. And also, let me see, does this next one here it talks about it. So this is actually very recently, within like the last 10 years or so, we found these intermediate black holes, and nobody really understands that. There are, let's say, the biggest stellar black hole, maybe 30 times the mass of the sun, 30, maybe stretching it, you can go out at about 50 times the mass of the sun. These intermediate black holes seem to be a mystery. These are objects somewhere between 100 to 1,000 times the mass of the sun. And these are, again, they're not supermassive, right? Because they're not 1 million to 1 billion times the mass of the sun, but and they don't exist at the center of galaxies. So they're just called intermediate, and we're still there. That's ongoing research. We're trying to figure out how these things form, whether it's the merger of multiple black holes. We really don't know. So here's another thing that I was kind of hinting at. In the year 1919, so this is just a few years after Einstein proposed the theory of general relativity, there was an astronomer that his name. He was a British astronomer named Arthur Eddington, and he went to Africa. I think it was in Africa to witness an eclipse, and he not just to witness an eclipse, which of course astronomers did back then, but to make a measurement, and the measurement that he was going to make was a prediction made by the general theory of relativity. That is, that if the starlight passed close to the sun, and normally you can't see the stars when the sun is out. Obviously, the sun is so much brighter, but the stars are there certainly. During an eclipse, you can see the stars that are relatively, if the starlight passes relatively close to the sun. Sorry about that. All right. So you can see the starlight that passes close to the sun during an eclipse. And Einstein's theory of relativity actually predicted how much the light would be bent. By what angle would the light be bent? In other words, this star over here would appear, because the starlight is passing really close to the sun, to be deflected by an angle. This one happens to be, 1.75 arc seconds. And so that's the general theory of relativity actually predicted what that angle was. And this guy named Arthur Eddington in the year 1919 took his team to Africa and measured this deflection. Because, of course, we know exactly where the stars are supposed to be. And this star shifted. And it shifted exactly according to Einstein's theory of general relativity, which made Einstein, super famous almost overnight. Because at that time, people hadn't really heard of his theory of special relativity. And just a few years later, he actually wins the Nobel Prize. Again, not for anything to do with relativity. It was for the photoelectric effect, for explaining the photoelectric effect, which has to do with quantum mechanics. All right. Another thing that Einstein's theory of general relativity did is, and this was actually, people started to notice this over the centuries. Okay, so this is not something you would notice right away. If you observe the planet Mercury in its orbit around the sun, it will shift by a very small amount, about 43 arc seconds per century. So the entire orbit shifts. And that has to do with the fact that Mercury is, of course, so close to the sun that it feels a little bit, it feels the gravitation and it feels the effects of general relativity. So the orbit does this slight shift, and people actually had measured this and noticed it. Like I said, because people had been measuring the orbit of Mercury for many, many centuries. And so Einstein's theory correctly described that. It described why it happens. So here's another thing that general relativity predicted, and recently we actually measured this. It predicts that, of course, light is what we call electromagnetic radiation, right? It's an electric and a magnetic phenomena that's what photons are. And what Einstein did is he predicted that there would be a gravitational radiation, or a gravitational wave that could be detected. Now, when he predicted this, we had no way of ever measuring that. Right? This takes extremely sensitive equipment that did not. You need like these really long laser, and you have to be very precise in the way that you measure this thing. And this, of course, it was built in the 1990s. This is called LIGO, a very famous experiment, which basically what LIGO does is it has these two lasers. Or it's actually, I'm sorry, I take that back. It's just one laser, and we split the light into perpendicular directions, right? So it goes off in this direction, and then it goes off in this direction, and then the light beams bounce back, and we look for what's called interference, right? So in fact, that's what this is: laser interferometry, interferometric gravitational wave observatory. That's what LIGO stands. That's what the acronym LIGO stands for. Oh, I'm sorry. That's right. So it was built in the 1990s, and I guess it went into operation in the year 2003. And for more than a decade, nobody saw anything with this thing. And we spent a lot of money looking for these gravitational waves. And of course, people thought that we'd be able to find the gravitational waves because all of the theory, all of the predictions that Einstein had made had come true, and had been verified through experiment. That's what I mean by come true. And so there was we believed that this was going to show that the gravitational waves exist. And of course, we did see this from the merger of two black holes. In the year 2015, there were actually two black holes, and LIGO actually measured that. It's two black holes that actually collided and merged into one, and this LIGO actually recorded. It turns out that gravity is the weakest of the four known forces, and these gravitational waves are extraordinarily weak, but LIGO was actually able to measure that. And I think recently we've actually measured things like a neutron star and a black hole interacting, and we can actually measure the gravity waves. So this is a complete, as it says here, a completely new window that has opened up to us on the universe, right? Before, we could only detect things in, for the most part, just electromagnetic radiation. There is some, you might have remembered we talked about neutrinos, right? These are subatomic particles that travel almost at the speed of light. We have neutrino detectors as well, and so that's an additional window. And this is the newest of them. These actually being able to measure these gravitational waves. Now, they can again, because gravity is such a weak force, you have to have an extraordinarily strong gravitational force between these two, between the two objects, for us to actually detect this with this experiment called LIGO. All right, so black holes exist. I mean, it's not. You're not going to find many astronomers nowadays that doubt that black holes exist. All right, so let's go over this in the next what do we got? 2 minutes. So supernovas leave behind neutron stars. So remember, these are type 2 supernovas. Neutron stars are extremely dense and spinning very fast, and they have very strong magnetic fields. The ones that are oriented in such a way that the radio beam sweeps in our direction, those are called pulsars. Remember, all pulsars are neutron stars, but not all neutron stars are pulsars, right? Because the neutron star might have slowed down, and we're not detecting that radiation, or the pulses are just not going in our direction, right? Let's say they're perpendicular to our direction. All right, so we've seen X-ray bursters and millisecond